In this video, we'll introduce the state estimation function in PowerFactory. Study case 1, undisturbed measurements should be activated. This network model represents a small distribution system at 3 voltage levels. We can see that there are a number of loads at 20 kV and 0.4 kV. There are no generators in this model, just a single external grid supplying active and reactive power. The state estimation function is used to obtain consistent load flow results based on measurements that have been imported into PowerFactory, such as branch flows and bus bar voltages. The states to be estimated might include the active and reactive power of loads and generators and the tap positions of transformers. At the core of the function is an optimization process, whose objective is to minimize the difference between the calculated load flow results and the measurement values through adjustment of the relevant element attributes. The state estimation function then provides the user with detailed reporting, which can be used to identify areas where improvements are required because the measurement results are insufficient or of poor quality. Let's first understand which states are to be estimated in this example. Starting with load objects and looking at the State Estimation tab, we see that both the active and reactive power are to be estimated. Likewise, the tap positions of a number of transformers. In a PowerFactory model, measurement devices can be created where elements are connected, and this project contains many such devices which have already been populated with measurement data. The network graphic can be colored according to measurement locations, and here the red coloring indicates the locations of the measurement devices. All the bus bars and other terminals are colored blue because the voltage measurement devices in the model have been made out of service. In this first study case, we'll look at the state estimation in a rather idealized situation, where good quality measurements are available throughout the network. The state estimation command is found in the Additional Functions toolbox here. For this project, we'll use a balanced load flow, but it's also possible to carry out state estimation for unbalanced networks using phase-wise measurement data. There are several components to the state estimation process. The plausibility check can be used to detect obvious errors in the measurement data. For this first study case, we know that we have good measurement data, so we've not selected any plausibility check options. The observability analysis step is used to detect regions of the network for which insufficient data are available. On the related page of the dialog, the user can configure how the observability checks are to be carried out and how the unobservable regions, i.e., where there are insufficient measurements, should be fixed. In this example, unobservable regions are managed using internally created pseudo-measurements which use the load flow settings from the related element as a starting point. Finally, there is the nonlinear optimization component, which optimizes the network until the best fit with the measurements is found. Part of this process is to detect and eliminate bad data. On the bad data detection page, the maximum number of bad data measurements to be handled and the tolerance factors can be set up. The state estimation process is iterative, alternating between the observability analysis and state estimation until a converged solution is found. Before executing the calculation, let's first run a load flow and look at the results, for example, at this line end. Later on, we'll see how the state estimation results compare with these load flow results. Now the command can be executed. Information about the analysis appears in the output window. no problems are indicated. The results that we see here are very similar to those of the earlier load flow. Note the dark green colouring throughout the graphic, which indicates redundant measurements. This means that there are more measurements than the minimum required to determine the state of the network. Such redundant measurements are still used, however, because they generally improve the quality of the state estimation result. No bad measurements have been detected. Now let's activate study case 2, disturbed measurements. In this study case, the measurement data is more reflective of reality, with some measurement values being suspect. This can be for various reasons, including faulty metering or synchronization issues. This is where the plausibility check becomes useful, as it provides a means of discovering measurements which are clearly erroneous. Such implausible measurements will be ignored for the purpose of the actual state estimation calculation. For example, a large power flow measurement should be ignored if the circuit in question is open at one or both ends. The command is executed. Looking at the output window, we can see that the plausibility check has detected some implausible measurements that are to be ignored. For example, one measurement device failed the test of having non-zero flow on an off-loaded circuit. Details of the plausibility check outcome can be seen in a Network Model Manager. The location of the device can be marked in graphic. Once the plausibility step is completed, the observability check and the state estimation are run in turn in an iterative process. Each iteration of the observability check allows bad measurements, i.e. those that differ from the estimated values beyond the required threshold, to be detected and ignored. These bad measurements are listed at the end of the process. In this study case, although there is some bad data, all regions are observable and so no pseudo-measurements had to be used. In the graphic, the pink colouring indicates where the bad P measurements have been detected. For a real network, the user would have to investigate the bad measurements and see how they could be rectified. It's also possible to write the results of the state estimation back to the database, i.e. into the respective elements, and save as a new operation scenario to use for further network analysis. Now, let's look at study case 3, unobservable network. In this study case, many of the measurement devices have been marked out of service to illustrate a situation where the measurement data is patchy. Looking at the colouring of the graphic before the calculation is run, we can see from the number of elements now coloured blue that many parts of the network do not have measurement information. This will result in unobservable regions. We'll execute the command. Again, a number of bad measurements have been detected. In addition, we can see from the output that unobservable states have been detected and handled by creating pseudo-measurement devices. The user will now have to decide what actions need to be taken to improve the quality of the input data. For a real network, the introduction of additional measurement locations might be required to ensure that all regions are observable. The PowerFactory state estimation function is mainly used in the context of automated processes. For example, as a custom development, it can be integrated with the user's own SCADA system. Another video about state estimation is available for the LV distribution network example, where state estimation in an unbalanced network is discussed.